It should be recording. But yeah, I think we can just get started. Okay, let's go for it. That's a little welcome. Okay, we can change that. Okay, there we go. Purpose of ASHRAE. If Christian, you want to get started?
Yeah. So the purpose of this standard is motivated by the environmental impacts of buildings. Now, we're just looking specifically at the US here. Buildings make up 40% of carbon dioxide emissions, 40% of energy usage, 13% of water usage, and 15% of the GDP. So they're quite a large market. So the standard's quite important because obviously there's a lot of environmental impact there. Switch to the next slide, please. So the purpose is to create buildings that can increase the environmental and economic performance over time, support the health of occupants, and in doing so, enhance satisfaction and the productivity of the occupants. This is achieved by site sustainability, water use efficiency, energy efficiency, indoor environmental quality, and then the impact on the atmosphere, materials, and resources. And all of these we'll go into more detail on each of these in the next few slides. So the basics is it provides a minimum design requirement for high performance green buildings. And it builds on some of the other codes, such as 55, 62.1, and 90.1. Now, these are not guidelines, but these are actually a standard, and ASHRAE believes they're an indication of future industry trends. So the mandatory elements of this are that it must be built on one of three things. The first is a brownfield, which is a previously developed piece of land. The second is a grey field, which is either an economically obsolete piece of land or an underused piece of land, or alternatively, an existing building envelope. What it cannot be is on previously underdeveloped land, having an elevation of lower than 1.5 meters above the elevation of the 100-year flood, or within 50 meters of any fish or wildlife habitat conservation area. As well as this, it's important that invasive plants are removed from the site prior to the construction of the new building. Can you go to the next slide, please? Thank you. So there are two major elements with site sustainability that need to be looked at. The first is the urban heat island effect, which needs to be addressed, and there are quite specific measures that need to be taken to do this. So the first one is that 50% of the site hardscape that is not covered in solar energy systems needs to have one of the following: either biodiverse plants, paving materials with a low solar reflectance, open graded aggregate, shading, parking, or a previously existing building that provides shade to this new building. Walls must be 30% shaded on the east and west, and any vegetation used to achieve this needs to be biodiverse. Roofs must also be 75% covered by either products with a low SRI with a low slope, or if the roof is heavily sloped, it needs a higher SRI. There are exceptions here for solar panels, heating, and walkways, and this is a good way to save money while still meeting the standard which promotes renewable energy systems. Finally, stormwater systems must be provided to the building site. This must be able to manage infiltration, evapotranspiration, rainwater harvesting, and stormwater collection use. It also must be able to achieve a discharge rate of the design storm in over 48 hours. And as well as this, contaminated soils are a big problem on brownfields and must be treated to limit the total suspended solids to 25 milligrams per liter.
So the next large part of this particular standard is water use efficiency. And some of the main things that are encompassed in this part of the standard are site water use, building water use, HVAC systems and equipment, and water consumption management. So the big thing when it comes to water use is you want to have systems that are put in place, like standards, that allow this water to be consumed the most efficiently it possibly can be. So some of the systems that are used in water use efficiency include smart water metering, which essentially just takes all the different inputs and outputs in water management and make sure that they're all balanced properly. So for depending on the site, if there's a lot of evapotranspiration or a lot of infiltration, this system will make sure that the water is used appropriately in the appropriate places. One of the big things, especially with landscaping and other water usages that are, are equivalent to a large portion of water use, is that they can only contain 1/3 potable water. So this means that when you use landscape areas and put water on them, you have to make sure that the water that's being used is mostly reused water, which, unless you have a smart system, is really hard to do because you wouldn't have the monitoring system in place. Another big thing with water efficiency is Energy Star. So Energy Star is a high efficiency rating that the US uses, which basically sets strict energy efficiency criteria and makes sure that you are optimizing the water usage inside of your building. So not only does this save water energy, but it also saves money, and it saves the money that goes towards your electricity bill. So some examples of things you can do to kind of meet Energy Star requirements would be one, replacing light bulbs for CFLs. And another thing that's to do with energy is using a 15% less and more efficient fridge, which allows you to reduce your total energy used in a household. Furthermore, a big part of water use efficiency is reusing and also collecting. So the first system that's really important is gray water, which is essentially when you reuse water that's already been used in your household. So one of the things you can do is you can take the water from different places such as the washing machine or anything that didn't have contact with basically solid waste or anything that's toxic. And so that water is collected and then reused in other things that have a lot of water usage, such as a toilet or anything that consumes a lot of water in your household. And then the other thing is the rainwater collection. So it's called rainwater harvesting. And this is super important because it basically allows you to collect potable water and store it in a cistern so that you don't have all of your water just coming from the city. You have water that's being collected and used through a system such as natural rainfall. And this will also cut down on your potable water. And between the two of them, this allows you to use a lot less water in homes. And it also is just more efficient in general because you don't have to take all water coming from the distribution system. You can just take water that's already been used in your house or falls on your land. The other really important thing about rainwater harvesting is that it also takes water away from the stormwater system, and that's really important because recently we've been having a lot of flooding. So it's really important to have this water also go into the building that it's falling on rather than just running off into the streets and flooding things.
So energy efficiency, as Christian said before, part of ASHRAE 189.1 is based on ASHRAE 55. No, ASHRAE 90.1, which is energy efficiency for buildings. So in terms of that, in addition to ASHRAE 90.1, we go into a lot of what ASHRAE wants for energy goals, I would say. So some of the energy goals that ASHRAE as a whole strives towards is for net zero energy and carbon by 2030, which currently our government is, I guess, going towards very slowly. Monitoring and progress based in standardized computer modeling. So that's just basically knowing how much usage we use in terms of all of our appliances. And the most recent goal is to have 189.1 reach net energy use intensity targets by 2020. That's this year, but obviously that doesn't mean officially net zero. It's just making sure that we have the targets that we want. Next slide, please. So if you look at the graph there, it sort of shows the relationship between 90.1 and 189.1, starting from early 1990s and everything. It's the energy usage across the world has declined due to the stringent standards of 90.1. And even with 189.1, we see a lot of large declines as well. The mandatory provisions for this specific category within 189.1 is on-site renewable power, as well as remote or automatically energy monitoring, as we'll go through later. Next slide, please. So on-site energy, renewable energy is basically a way to power your building while reducing its reliance on fossil fuels and minimizing greenhouse gas emissions. So specifically, on-site renewable energy could mean PV cells, solar thermal, geothermal, wind systems, or any combinations of those. And specifically within this category, we want to provide 20 kilowatt hours per meter squared times the gross roof area, specifically because it's so much easier to provide these energy systems on a larger surface within your building site. And most times the only area available is on the building roof. So as well, specifically if you have a lot of energy efficiency equipment that meet the applicable Energy Star requirements, as Marco talked about in water efficiency, which also apply to energy efficiency as well. You only need 13 kilowatt hours per meter squared times the gross roof area in order for the roof on-site renewable energy systems to be applicable. So on-site renewable energy play a very important role in obviously meeting household energy needs throughout the community as well. Next slide, please. So energy efficiency in terms of automated demand response is a very important aspect in terms of monitoring energy usage. So devices that need to be used communicate the energy consumption data to a data acquisition system, and that way they provide daily data and record energy profiles. And so through this automated demand response, the data is used to make sure that energy is not being used when it's not needed, and a lot of the cost demand should decrease. If you can see from the graph there, that's the red line is what a normal electric grid demand curve looks like. Obviously, we don't like having that peak there because it represents, big loads during a short amount of time, and a lot of people want to use the energy during those times, so it's very expensive, and it takes energy factories to create more energy at a higher cost, which is very inefficient. So instead, you want to shave off the peak and using voluntary curtailment from a lot of the manufacturers, as well as building management. We're able to decrease the peak. Next slide.
Okay, so I think this is me. So indoor environmental air quality. So mandatory provisions for this include outdoor air monitoring and tobacco smoke control. And then it also addresses areas such as thermal comfort, and envelope acoustical design. So I'm going to be hopping in to talking about the indoor air quality and how this can enhance the essentially building occupants' health, and why it's important to maintain good air quality. So essentially, air quality is determined by the concentration of particles and gases within the environment. So why is this important, even though air particles are really, really small? Well, while the particles may be puny, it's really important to take care, or to, to take care of the air quality, because it contains a lot of chronic illnesses, and it carries a lot of health issues that can affect your health. So to improve this, there are several ways. The first one includes air cleaners. So air cleaners essentially is a device that removes contaminants from the indoor air quality to essentially improve it. So benefits for this include for people with allergies, because it removes the small allergen particles from the air. It's also good in removing other harmful particles, both chronic and acute. It also removes secondhand smoke. So that's really, really important. However, some difficulties, it really depends on the model and it depends on the type of unit. But essentially it can push back the contaminated air and collect more contamination, which is not good, and you don't want that. The next one includes UV lamps. These are actually really cool. So they're essentially ultraviolet lamps that use like UV rays to kill bacteria that are found on surfaces, and like molding that can be found in indoor air environments. So our last workshop was actually on HVAC systems. So if you guys attended that, you would know a bit more about it, but UV lamps can be used to kill the bacteria found in HVAC systems, because you want to keep your HVAC system nice and clean. So the coil specifically found in HVAC systems can contain a lot of bacteria. So if you keep your UV lamp close to it, then it can essentially kill these bacteria before getting into the air that occupies the building. So that's really, really cool. Also, a fun fact, so apparently there's been not lots of talk, but some talk about implementing a UV lamp or UV lamps in indoor spaces to reduce the spread of COVID. However, this might not be as effective due to UV lamps needing direct exposure to the virus. But yeah, that's in the air right now. So that was just a little fun fact for you guys. And then the last one I'll be talking about that can help improve indoor air quality are humidifiers / dehumidifiers. So back on HVAC, because we love HVAC here in ASHRAE. So in the winter times, HVAC systems usually have higher temperatures. So it dries the air inside the building or home. So by having dry air, this can actually lead to respiratory issues for occupants, which is not good, because that's not good for your health. So humidifiers essentially adds humidity to the air, usually in the colder seasons. And the ideal range for humidity is about 30 to 40% for buildings, for you to be like comfortable. And then dehumidifiers do the opposite, of course. So it removes humid air from, sorry, let me rephrase that. It removes humid air in the warmer months for colder countries, because humid environments can actually be a breeding ground for bacteria. So we want to take the humid out as much as possible. And then, okay, there we go.
Yeah, and so I'm going to be talking about the impact on atmosphere, materials, and resources, because we want to be sustainable. And the mandatory provisions here, as you can see, are construction waste management, no CFC-based refrigerants, and recyclable storage areas. Next slide. So I'm now going to be talking about how we want to promote our sustainable materials. And as you may know, industrial buildings nowadays are made mainly of concrete. And producing and manufacturing this concrete requires a lot of embodied energy. And what embodied energy is it's basically all of the energy that is required in the process of creating a product from start to finish. And using a life cycle analysis, you can see that you can see all the emissions that a product creates. And from this, you can see that concrete creates lots of embodied energy, which is unsustainable. And now I'm going to talk about some sustainable materials that we could use for construction. And one commonly used one would be timber. And as you can see on the right, it's used in mass timber construction, where the building is entirely made of strong fire-resistant wood. And the difference here between mass timber and concrete is that it actually weighs one fifth of the concrete building, meaning that it actually reduces the embodied energy. And another plus would be that timber use is sustainable and it would absorb carbon dioxide as it grows. So the next one would be straw bales. And this one is a bit weird, but it has been becoming more common in small buildings. And what it does is basically it's used inside building frames and it can be used as insulation, platter, or gypsum, and can provide a high level of insulation. And quite obviously, the benefits is that because it is using straw, this material is very cheap and sustainable, and it's also easily renewable. So next one would be grasscrete. And this is basically concrete, but just less of it, where greenery and grass is able to grow on the concrete of floors, walkways, sidewalks, and driveways. And the main benefits here are that we can reduce the amount of concrete and reduce the amount of embodied energy. And also this improves our stormwater drainage and absorption. The next one is hempcrete. And this is basically another form of just modifying the concrete. And it keeps its performance levels, but it implements sustainable materials inside of the concrete. And how it's made is fibers from hemp plants are bound to the lime during concrete processes, and this creates a sustainable building material that we can use. And the last one is recycled plastic. And this allows for a lightweight solution that reduces embodied energy of concrete. And since it's a reusable material, it offers flexibility in designs, and it's easier to mold so that you can get the concrete shape that you want. And in general, after talking about all of these sustainable materials, the main objective here is that we want to keep the structural integrity of buildings, and any sustainable material can be used as long as it has high strength and good performance.
So now we'll be presenting a capstone project from last year, and this one was actually done with my teammates Will Banks, Noah Cassidy, Ivan Priono, and myself. And it was about designing a high-performance home in a native community called Attawapiskat, Ontario. So we we designed the house in terms of the standard, but also a lot of other things. But today we'll just be talking about how it could be relevant to the ASHRAE standard as well. So the problem that we were given was that there is a native community called Attawapiskat in Northern Ontario. So as you can see, it's really, really far from U of T. If you try to Google how to get there, it says the fastest way to get there is 15 hours by flight, and that's from Pearson and then a whole bunch of other airports in between. So safe to say that it's a really remote location and transportation up to the site is really difficult. It also has a really harsh climate just because it's in Northern Ontario. It's also kind of like a flat plain. So there's lots of wind, lots of snow, and it's just not as warm as Southern Ontario is. So the main issues that we were also given were to deal with the native housing crisis up there. So for those who don't know, native communities actually have a lot of overcrowding issues just because lots of families of on average, 6 people per family. They live in these houses, pretty much sleeping in the same room as their siblings and their families and parents. And this also causes a lot of respiratory illnesses because of all the mold and things like that grow in the houses. And this also leads to the mental health issues as well, just because they're kind of in these confined spaces, don't really have a lot of place to have any privacy. So these were kind of the things that we were dealing with when we were given this problem. Also, so just numerically, we were given 100 square meters to design the space, so still not that big. And we needed to keep an annual heating demand of 40 kilowatts per hour per meter squared and an annual energy demand of 80 kilowatts per hour per meter squared. Also, we'll kind of be touching on a potable water system that we also kind of implemented into the system, but I will let my, my partners also talk about that a little bit more. So the first part was how we addressed the reducing emissions. So like we said, the Native community was really far north. So if you think back to the life cycle analysis about these things, if things are built out of embodied energy, just transporting things also emits a lot of greenhouse gas emissions. So one way that we tried to reduce this was making one trip with all of our materials in it. So that required us to have 4 trucks, 1 train, and a barge to get all of our goods up to Attawapiskat. So it wasn't just a 15-hour flight. But this also reduced the amount of trips that we would take to get there, which also reduced the greenhouse gas emissions. Another thing that we addressed was the enhancing occupant health and comfort. So one thing that we talked about or implemented was a heat ventilator, which we had covered in the previous workshops. So this is the HVAC system that expels stale warm air into the outdoor environment, but as it pulls in new fresh air, it mixes with the outgoing warm air. So it captures the temperature of it so that when it comes into the home, it's fresh air, but it's also warm. So this reduces your heating costs, but also just makes the environment a lot warmer. Another thing that we used was a wood stove. So this is partially because of cultural practices, because Native communities do a lot of cooking with just natural fires and things like that, but it was also a faster way to heat up the home in the winter seasons, just because it is such a harsh climate. So we would need the heat to be a little bit extra during those times. Another thing that we had to deal with was the foundation. So the home was actually on an active layer of soil. So how we addressed this was by using a triodetic foundation, which is just basically something that moves along with the soil so that the home doesn't feel like it's moving at the same time. We had windows on the south side of the home, which and that was because you mainly get a lot of solar heat gain from the south in Canada altogether, or just in the northern hemisphere. So by putting windows on that side of the home and having a large space, we were able to take the benefits of the sunshine periods during the day for that as well. And I'll pass it on to my teammate Ivan, who will talk about the programs we use to get these analysis done.
Hello? Is my mic okay?
Yeah.
Awesome. Yeah, so my name is Ivan. Thank you, Simone and ASHRAE, for having us here to speak today. Yeah, so I'll be talking a bit about the software that we use to kind of figure out which materials we were going to use for our building enclosure and our envelope, and just kind of the process, the inputs and the outputs, and how we use the information that we got from the software to kind of come to our conclusions. So the 2 software that we used for our project is Therm and Woofy. You guys will probably work with those sometime in your undergrad if you continue taking building science courses. So starting off with Therm. Therm was a software that we used to assess the thermal performance of our building envelope. How Therm worked was you just kind of drew out the assembly, the layers, and the framing as well. And the main reason that we wanted to use Therm was because Therm did a good job providing an accurate R value of our building envelope. In undergrad, the main way that you learn to calculate the R value is through one-dimensional analysis. And what Therm did was, it was more of a 2-dimensional analysis, which came in really useful when you have things like studs for the framing that acts as thermal bridges that has a heavy 2-dimensional impact. So as you see in figure 29 here, we have a stud or a framing member there at the end. You specify the material properties through Therm, and then you just let Therm simulate and do its thing. You'd use Therm on the floor, the roof, and the walls. And the output that you get is the R value. It's seen in the bottom there of figure 29. And alongside the R value that Therm provides, you also get a nice little thermal contour of the wall. which was, it's interesting to show. For our capstone project specifically, we were mainly looking for the R value of the building enclosure, but having the thermal contours to kind of have an idea of how the temperature change throughout our building envelope was also pretty useful to show. Yeah, and Woofy's hydrodynamic modeling software. So that just kind of keeps track of how moisture travels through the building enclosure and through the wall. So because our location is at Awapiskat, location very north, during the winters, you have a crazy temperature gradient between the inside and the outside, right? Like, I think our targeted temperature difference was like 40 degrees Celsius. We wanted to maintain 20 degrees in the inside, but the temperatures on the outside would go to, you know, colder than -20. So what happens when you have a really big temperature gradient like that is you have huge vapor drive and air drive as well, air and vapor moving throughout your building envelope. And what happens is that that air is also going to carry moisture along with it. And what we wanted to ensure was that the building envelope that we created would prevent bulk water and also vapor from condensing within our walls and accumulating, because when water accumulates in our walls and you don't let it escape, that's very detrimental to our building enclosure, especially for a house like this that uses wooden frames. You know, after a long time, you're going to get your wooden components rotting, right? And you don't want that. Yeah, so the way that Woofy works is like Therm, you specify the different layers and its properties, and you simulate it for however long you need to. It looks like here in figure 31, we simulated it for a 3-year period from 2020 to 2023. And what's shown in that graph there is relative humidity is shown in the green line, and we have temperature with the red line. And yeah, what we're looking for is we just want to make sure that the relative humidity in the wall doesn't reach or exceed 100%. When the green line reaches that point, you know that condensation is happening in our walls. So as you can see in figure 31, it never reaches that point. The maximum is around somewhere in the 50s, which is pretty good considering the temperature gradients that we had to work with. And yeah, you notice that you have the spikes in the winter as expected, but you also see that it goes down eventually in the summer. So that shows that our building envelope allowed the wall to dry. And that's really good because we don't want any water accumulating. And yeah, that's what you'd be using Woofy for. Very useful software. And yeah, that's about it in terms of the analysis software that we use for our walls. And I think I'll pass it over to Will now, who's going to talk about the potable water.
Thanks, Ivan. So yeah, transitioning to water. So in Canada, we tend to take clean drinking water for granted, but there's actually 61 long-term drinking water advisories for public systems on Canadian reserves. This is something the federal government is trying to tackle, but it's been years and there's still many advisories. So Attawapiskat declared a state of emergency last year over excess levels of a couple chemicals which pose cancer risks. And in addition to that, the town has had drinking water issues for decades, and elders would comment that they don't remember a time that they could ever drink the water from the tap. So some of these issues are pretty obvious. If you look at this photo in the slide, the drinking water source is essentially a swamp. And we tend to think about high-tech solutions as engineers, and there are many great innovative products, whether it be glazing or building materials, in this case, filtration systems. But you always need to be careful about context, and especially with a remote community, you need to make sure that your solution is feasible, both in cost and in implementation, and especially in maintenance, because if you implement a high-tech solution and it has a problem, if, say, that problem requires specific knowledge, you can't be you know, flying someone out from Toronto to come to Attawapiskat all the time to fix something. So several efforts were undertaken to address this issue, including membranes and granular activated carbon, which would remove organic material. But these weren't feasible in every home. They're expensive, relied on a single manufacturer, and again, you can have maintenance issues. So we found that basically the water crisis required a total overhaul. So in addition to water quality itself, we found that community demand is more than twice the capacity of the local water treatment plant. So essentially they have a broken system, and you need to go to this source instead of an end of pipe solution here. So we recommended to have a whole new water treatment plant and to move the water source upstream on the Attawapiskat River. So that about covers it for water. And I'll just mention too, I did the renderings and some 3D modeling for the project. And I'm a big fan of Rhino and Grasshopper. If anyone's ever checked those out, and if you're interested to learn more about those, can reach out to me. Thanks.
Thanks, Will. Another part that we covered, or sorry, this wasn't covered in our specific design, but something that came up in our research was the sustainable materials that Andrew had mentioned earlier. So the straw bale homes is actually something that's used in Native communities a lot. Again, because of its high thermal insulation characteristics, I guess. And also our home was made out of wood primarily. We had the wood stove. So just ways that we kind of addressed the sustainable materials were these kind of innovations, but no, we did not use straw bale homes because we needed to, our thermal insulation was, we just used something else for it. But next slide, sorry. And so the building quality, how we measured this was using something called HOT 2000, and I will pass it on to my partner Noah to describe what we did with this one.
Yeah, okay, so in the end, when we were, so the part of the project, like Simone mentioned at the beginning, we had a couple constraints. We had our cost constraint, but our other big constraint was the energy demand, or the energy use intensity, so the kilowatt hours per meter squared of floor area. And so instead of doing some manual calculations and trying to figure it out ourselves, we stick everything into this program called HOT 2000, and it spits out a number that tells us how well our design is performing. And so so you can see this little rendering. So the rendering is done in Rhino by Will. I would just like to point out how pretty it is. It's a very nice looking picture. But we use HOT 2000 to estimate all these numbers surrounding it. I just wanted to take a moment while we're talking about this to emphasize how our design process worked while we were going through all of these choices that we have to make. So for our project, we had this limit of 40 or 80, it was 80 kilowatt hours per meter squared annually, I think is what it was. And so, we would make a bunch of design choices, and we would throw together a bunch of things, and then we would stick it in HOT 2000, and oh no, we're over the limit. What are we gonna do? So then we have to go back to our design, make a whole bunch of other changes, stick it back in HOT 2000. And we did that several times, over and over and over again. And so the point is just, it's very iterative. Obviously, like you're told constantly throughout engineering, it's an iterative design process, and you have to try a few things and keep iterating on your design. So specifically, I mean, the windows, we spent a long time changing the window dimensions and the placement of the windows and what side of the building they were on and we shrank them several times. So you can see there's kind of big windows on the front side to take advantage of those solar gains from the sun and the orientation of the building in the community. but you can also see there's only a couple tiny windows on the right side, and it's similar on the left. There's only a couple tiny windows there. I don't think we ended up with any on the back. And so we kept shrinking them and shrinking them until HOT 2000 worked out. So HOT 2000, it's kind of a primitive program. Generally, the industry standard is to use Energy Plus, from what I've gathered. But we're using HOT 2000. You have to find weather files for your area, which is a whole other struggle in itself. Trying to work with the very old standards that HOT 2000 and I think Energy Plus use for weather files. I'm trying to get that work in the program and trying to find a weather file that accurately represents your area. All these things take a lot of time, and they're a huge challenge. But to get an accurate model, you need accurate data, so it's kind of worth it. You're going to input your weather files, your window to wall ratios, your materials that all your walls are made of, and the thicknesses of all the stud placement, and all these separate things. And you build a little model of your home, and then it spits out some numbers. So you can see here, this is our graphs for the total energy demand in the end. So you can see our peak energy usage was in the winter, which makes a lot of sense, with 10 kilowatt hours per meter squared. And you can see from the chart on the right, a little breakdown. You can see there's a lot of hot water heating. I think, so this was, yeah, so you can see the heat pump is very active in the winter and obviously not in the summer. We had to supplement so we use a heat pump as our main heating element. We had to supplement some of that heating with the stove. So it's not a carbon neutral design, but the stove, like possibly Simone said, is something that's favored by the First Nations communities. It's something they like to have in their buildings, and we talked to a couple of representatives from the community who said, yeah, they would like to, who were actively recommending wood stoves and seemed like they were in favor of them. Yeah, so we have supplying the heating demand. We have the stove and the heat pump. And we've got an HRV that runs in the winter and the summer to meet some of that cooling and heating demand as well. And the heat pump also runs in cooling in the summer as well, actually. Other than that, it's pretty constant demand for the lights and appliances. I mean, that's a decision we made in the simulation, that it would be a constant demand throughout the year. Yeah, I think that's all the important parts of HOT 2000. Yeah, I mean, I can keep talking, or Simone, you can just...
Yep, thanks, Noah.
Okay.
And so the last part of the standard was how you can make your buildings resilient to some natural hazards. So one thing that we did was we implemented a porch element on our north side of the building, which was kind of northwest, I guess, because of the tilt that the house had. And what this did was it basically just helped with to add an extra unconditioned space for prevailing winds that are in Canada altogether, that come from the north and the west. So what this did was it just acted as an extra barrier so that the house the house enclosures wouldn't get the direct pressures of the wind, and again, just sort of minimize the pressure drive and effects of the natural hazards of wind in this area, and also snow, I guess. And another thing that we did was the impermeable vapor barriers, and this was implemented in all of our enclosures. So this was just to make sure that all of our enclosures were as continuous as possible, because the second that you have an air leakage anywhere, it's just sort of a small space that all the air wants to rush through, and that can become super detrimental to your design altogether. And yeah, so that was our Capstone project, and how it kind of applies to this ASHRAE standard. If you have any questions specific to the project, you can ask my teammates and I, but I believe this is also the end of the presentation.
Feel free to use the chat or use your microphone if you're comfortable in asking questions. Also, thank you so much for all the Capstone presenters for coming out today. That was really, really cool, and learned a lot about different softwares that I personally did not know about. So that's awesome. But yeah, feel free to use the chat or microphone. I believe we do have Cajun here who wanted to make a quick announcement, if I'm not mistaken. But yeah.
Before that, I had a quick question for Simone, I think.
Yeah, go for it.
You mentioned during the capstone that the house was built on active soil and there was something you did to mitigate that. What did you say that was called again?
It was a triadetic foundation, but I think Ivan, if you want to answer that, because he actually kind of researched a lot about that.
I could talk a bit about triodetic. It's actually like a trademark name. It's not like a specific name of like a type of foundation. It was just like a brand name, a company name. So like Simone said, we were working on an active layer, and we just wanted to maintain the integrity of the building envelope, which would have been affected by differential movement of the soil. And the way that the triodetic foundation worked was that it was basically a truss system. And any changes in the ground that would have occurred from seasonal changes, the truss system would have been strong enough to support the load of the building while the ground actively changes. So that's a bit about how triodetic worked.
I think it's called multi-point. I think that's what the...
Interesting.
Yeah, multi-point, right.
Yeah, I was just looking it up here.
Yeah, so you can see it on the picture on the slide right at the bottom of the building.
Oh yeah, shout out to Will for making all our renderings. These are actually really, really hard to do, but he spent quite a lot of time on these. So yeah, this is how our house looks, or theoretically.
She's beautiful.
Thank you. Or Will, that's on you.
Are there any other questions? Thank you for asking, by the way.
Oh, thank you for answering.
If not, I'm gonna skip just two slides. Okay. So yeah, like Simone said, this is the end of our workshop, and we're very appreciative for everyone for taking their time coming out today, especially during midterm seasons. We understand it's very, very busy, or PY or whatever you're doing. It's just a busy time. So we really appreciate it. If you're not signed up actually, before I even get to general member list, you can sign up if you're interested as an ASHRAE International and ASHRAE Toronto chapter member. So basically ASHRAE holds a bunch of different workshops on a variety of topics. And if you sign up as a member, which I believe is $32 total Canadian, you can go to a bunch of workshops and social networking events for free. Yeah, moving on from that, you can add your name to the general member list to, I believe Margot sent a link at the beginning of the workshop, not conference, at the workshop. So feel free to sign up. You'll be getting Zoom links along with the recordings and of our workshops. And yeah, follow our socials at ASHRAE UofT and all that good stuff. But yeah, I think I will give the floor to Cajun. I believe he's here to make a quick little announcement.
Yeah, can you guys hear me, see me? I hope you don't see me though. But can you?
Yeah.
You do?
We
okay, well,
we can see you too.
okay, yeah, I figured, but I'd rather, yeah, you guys know. So first of all, I think I want to thank the ASHRAE UofT Student Branch for organizing all these workshops. I think what you're doing here is a great job. Having all these different codes, which are some of the most used codes, was a great way to kind of give back to the students, and kind of it's a resource that, you know, seeing it now, I'm thinking, you know, why didn't we do this like for the last 5 years? And I feel like I'm really grateful that you guys have got this going and that it's being recorded. I think this is something that we should definitely keep moving forward. And I know that some of the student branches have been invited, and there's some members here from different student branches, and I think a lot more of them need to come to these because these are super informative. And I also want to thank the Capstone team. You guys did a great presentation. Like this whole presentation was really high quality. I'm not sure how long it took you guys to organize this, but if it was 2 weeks, wow, that's really amazing. It also kind of gave me some nostalgia because I was a part of the Solar Decathlon China team, and seeing all this kind of gave me some flashbacks, like, wow, modeling and looking at different ways to design buildings and cost analysis. Wow, this is like it's a kind of a good nostalgia. Like I'm not really having any PTSD, which is good. You guys really delivered a great presentation, all of you. But to talk about ASHRAE, so I am the ASHRAE Student Activities Chair for Toronto, the Toronto chapter. And like Annie, was Annie, right? Because I'm sorry, kind of going late and I didn't hear any introductions.
Yes, hello.
But if
Yeah.
that was, okay, so yeah, Annie, so she kind of mentioned that there's free events at the Toronto chapter, which is exactly right, which is why I think it's a great time to join the chapter now, especially because of the pandemic. You can kind of take it because of the pandemic, because you can kind of take advantage of all the webinars that we're going to be posting, and they're all free to all members. And there's a lot of beginner workshops, and I want to restate the idea that you'll have all the events for the rest of the year free. So that's a lot of events, and we're also going to be piloting a lot of Zoom breakout rooms for networking events. So if you guys want to take advantage of that, I think it's a great opportunity to do that by joining the society and then joining the branch or the chapter. And as a student, you don't have to pay any extra dues, which is so like you'll have a flat fee of about 30 something USD, like Annie mentioned. And from what I understand, the U of T chapter, the U of T branch is also kind of sponsoring students, if I'm right.
Yeah.
Yeah.
Yes. Yes.
Yeah. Okay. So yeah, it's definitely something that we're taking advantage of, because something that people might not know is that we also sponsor students. The Toronto chapter sponsors students to go to conferences every year. This year, obviously, there's going to be no physical conference. It would have been, so the winter conference has a student program that is worth attending, and I think a lot of people in this, not a lot of people, but some few people in this call have gone to the conference, so they can definitely vouch for that. It was a good experience. I hope. So there's going to be some more sponsorships this year because it's online. It's going to be more affordable, so we can send more students, but you have to be a student member of the society for us to want to send you, because you get a discount to the conference that way. So I think it's worth signing up, because we'll have a lot more spots, and that means there's a way better chance of you getting sent to a conference. And even if you don't get picked, the conference fee is $25. So if you get sponsored through the U of T chapter to be a member and get sponsored to go to the conference, it's a win-win, and you get a bunch of free events. It's a win-win-win. And on top of that, there's a bunch of scholarships that not the Toronto chapter, but the ASHRAE Society has up for grabs right now. And the deadline is December 15th for some and December 31st for others. If you go on the Toronto chapter website, there's a whole student page where it gives you a big walkthrough on how to go about applying for these scholarships. And if you want to get involved in the society, if you want to get involved in the chapter, it's a great way to meet people. I get it, it's hard, especially during the pandemic times, because meeting people in person is a lot more, I guess, fruitful than through a screen. And like not everybody's shaving. You might notice. I hope it's blurry, but I hope you might notice that it's not always like easy to kind of. You don't have to actually be as prepared. You don't have to be in a suit anymore. No one's going to be judging you, so that's great. You can just kind of be yourself. But there's a lot of opportunities, I think, in the Toronto chapter and society that if you guys want to get involved in, you can reach out to me. If you're not even sure if you are going to get anything out of it, reach out to me, and I can probably give you a rundown. I can listen to your perspective, your story, where you're coming from, where do you want to go. We can see how you can fit in, and if you don't see that you can fit in ASHRAE into the ASHRAE chapter, the ASHRAE Society, reach out anyway. I can probably help direct you to a society or organization that's worth joining. Because as a student, especially in times like these where it's going to be hard to get a job after graduating, it's going to be a lot more helpful to have volunteer experiences or just involvement in societies and organizations on your resume, just because that's kind of how I got a job, so I can vouch for that. And if you have any questions, reach out to me or Margot or anyone in ASHRAE, and I can tell you they're all really nice people. I've been a part of it for like 4 years, and if it wasn't for one person just randomly reaching out to me and say, "Hey, why don't you join ASHRAE?" And I go, "What is that?" Okay, fine. And now I'm here doing these talks. So crazy how the world works. But yeah, that's pretty much my spiel. Hope convince some people.
You've convinced me and I'm already in it,
Yeah.
so. Thank you so
Thank
much.
you, Kajan.
Good.
I
Thank you
appreciate
so
you coming
much.
and talking.
No
But
problem.
yeah, that concludes our workshop, our second workshop. Thank you so much, Cajun. Thank you so much, the Capstone team. It was definitely a fun one for sure. But yeah, our next workshop, if I'm not mistaken, is on indoor air quality ventilation indoor ASHRAE. I know. Did I pause? Am I frozen? I'm not
Very
sure.
good.
I forget the
Yeah, you're
code.
good.
Is it ASHRAE 55? ASHRAE 55.
It's not ventilation air quality. It's all good.
Okay, I froze for a second, but yeah, feel free to head out and enjoy the rest of your night, morning, afternoon, wherever you may be. But yeah, thank you so much, guys, for coming out. I'm gonna stop recording.
Thank you for organizing it.
Thank you.
Thanks.